So, as I said in our previous class, it is very, very important that you do understand your power factor correction. So, in this class, we are going to work with power factor correction using capacitor banks. It is important to do understand calculations which can be made on the adjustment from what we had in our previous class. So, I want us to consider, remember, we had this power triangle in our previous class. So this power triangle is going to be adjusted depending with the method that you're working with on the power factor correction. All right. So this method that you're working with is the use of what? Capacitor banks, which are static capacitors. All right. So the capacitor banks, these are simply static capacitors. All right. So we are going to have static capacitors being connected to our induction motor. Remember, we are saying the induction motor has got what? A poor power factor. So when the power factor is improved, we are going to see changes that are going to happen in terms of our power factor being what? Improved. But the major concept is, what are you using? Using what? Capacitors. So a capacitor bank is made up of two or more identical capacitors. They're supposed to be two or more. Two or more identical capacitors. Identical capacitors. Same. They're supposed to be same in this case. Same capacitors connected in series or in parallel to each other to store electrical energy and is stored for power factor correction what purposes. So that is the condition of the power these capacitor banks. They're identical capacitors, same capacitors, either in series or in what? In parallel. So the effect, what will be the effect? We are going to notice for a single phase and also a three phase, depending with what you'll be having. But in our major case, we just want to consider what exactly is it that we are going to have. The capacitors, all right, they're just connected this way, guys. Before we talk of the effect to our power triangle, we'll be having a load. Let us just consider a simple, which is what? A single phase. So this is our supply. All right. And this part, we are going to have our load. So that's the condition. So remember, live and what? And neutral. So we just have the live and what? And the neutral as you just consider single phase. So this is our condition, guys. We are going to have our capacitors being connected. So it is just like capacitor banks. We are going to have our capacitor connected. So let us just say in series like this. All right. These capacitors will be connected in series depending with the number of capacitors that you'll be having, but they'll be what? They will be in series or in parallel. That is the condition of what? A capacitor bank. A capacitor bank. So that is the condition, guys. That's what we're just talking about. So when it is connected or when these capacitors are there, so as a single part, we are calling what? A capacitor bank. Capacitor bank, we are talking about those capacitors connected together. So I'm just referring just a capacitor what? Bank. So when a capacitor bank is inserted or it is being connected, we are going to notice that on our power triangle that we had before, remember this is what we had previously, we're having something like this. We were just having our triangle, guys, as we had, remember we're saying we're going to have our triangle this side because of what? We are dealing with an induction motor. We have got what? A lagging power factor. So we already know the presentation of the triangle, how it is going to be like. All right, so our triangle is supposed to be like this. So in a normal presentation, this is what we're going to have. In a normal presentation, where nothing has been inserted. Originally, this is what we had. We had our true power, we had our apparent power, and this part, the whole of this part, was representing our reactive power, which is Q. But in this case, we have inserted the capacitors and the power factor has been improved. So we are going to notice that there will be a change in this phase angle that was being given. The whole of this phase angle that we had, was this was from the original conditions that you had. There was a phase angle that was going with these conditions. We had what? A phase angle there. But after this capacitor bank is being inserted, we are going to notice that there will be a shift. So this is what we're going to have at the end. All right. Remember, guys, this will be at what? At 90 degrees here. So the change that we are seeing is giving us a new phase angle. We are now having a new phase angle. So I want us to see what exactly happened here. This is our original diagram, this one. The outer triangle. This is our original diagram. So we are going to notice that as these capacitors are being installed, previously, we were having this part as our apparent power. This was the load. This is the load kVA, the one that you're given previously, this one. That's our load kVA. But as we have inserted these capacitors, look, the line that we're having, this hypotenuse, it is now here. It has shifted from this line. We are now having it here. This is our S2. So let us just say this is S1. So you're going to call this S2, which is now our resultant kVA. So this will be our resultant kVA. The same is affecting our reactive power. Remember, the whole of this part from the outer triangle, the whole this part here, this was your reactive power. This one, the whole of this part was representing our reactive power, the whole part. So let us just consider this part this way. The whole of this part, this was our Q1. As we considered, say, the original values, every part which is from the original values, let us just refer it with what? With 1. For original values, let us just use what? 1 to denote our original values. We're going to denote with what? With a 1. Then the one that after the new values now, after the capacitors have been what? Inserted, we now have what? New values. So these ones we're going to denote with what? With a 2. The new values after what? After the capacitor bank is inserted. After the capacitor bank is inserted or installed. When it is installed, these are the values that you are referring as the new values, denoted by what? By 2. So you are going to notice that when this part, when our capacitors are being installed, all right, we saw that our apparent power is affected. What about the reactive? The reactive power is also affected because due to this phase angle that we have there, we are going to notice that it is giving us here, this part here, which is our Q2, this part. The new, this one, the new value for our reactive power. This is due to this phase angle that we see. This one is due to this phase angle one that we see there. So what about this one, which is not due to any phase angle? As you can see here, there's a difference here that we see. It is not due to any phase angle. Guys, let us be clear here. This one, remember, Q is equal to what? Q is equal to VI sine of phi like this. So it means if I have V and current to calculate Q2, I was going to use those voltage, current, and the phase angle that I'm using there is 2. If I was to calculate Q1 in the same sense, I was going to use V1 sine phi 1 like this. The angle that I was going to use is this angle and this one. But what about this one that is remaining here? There's another part here that is in between this point here, in between. Which angle are we going to use? It was going to use the difference between these two. But take note, it is no longer in a right angled triangle, just like these two. It was happening that we are using these two, guys. This one is from a right angle concept. It's from a right angle concept that we are applying there. The trigonometrical ratios were being used here. So it means it was going to be impossible for us to calculate this with the trigonometric ratio. We're not going to have any formula like this to calculate this part that is remaining here. So the only way to have this part that is remaining is to find the difference between these two, Q1 minus what? Q2. Because Q1 can be calculated, can be determined. Let's say they are there. We just subtract Q1 minus Q2, we have this part. So what is it, this part that we are seeing here that is even remaining, that we are just saying, this part that is remaining, this part, what is it that we're talking about? This whole section or this whole region or the space that is remaining here from these two, Q1 and Q2, this part that is the one that I'm indicating here, is the one that is for the capacitors that were being installed. That's our installed reactive power, this one. This is the one that we refer as our installed reactive. That's our installed Q or installed K VAR. Remember, reactive kilovolt ampere reactive. The rating of the capacitors that were being installed, the rating of what? Of the capacitor bank. This one. The one, because we inserted the capacitor bank, remember. So this is the rating of what? The capacitor banks. The rating of the capacitor banks. Of the capacitor bank, I mean. So, guys, this is the important part because that is the one that we are talking about. This is the part, this one. As you can see, there's no formula for us because we do not have the angle that we can, unless we are to use any other mathematical calculation, use of your trigonometrical ratios. It is up to you how to find this. As you can see, it's a right angled triangle. So you're going to use your mathematical calculations to find that. The installed kilovolt ampere reactive, which is our reactive power for the capacitor bank. So it is very, very important for you to calculate that. So using these, maybe it can help us. Let us just say we've got points. Let us just say this is our origin. Remember, this is taken from O, the origin, all right? So let us just say this is our point O to point A. Here we call this point B, and we call this point C. The part that we need, which is the rating of the capacitor bank, is this one, BC, the rating of the capacitor bank. So to calculate that, all right? So for our calculations, the rating of what? Of the capacitor banks. The rating of the capacitor banks, all right, which is BC, according to my diagram. It depends, maybe your diagram you set as A, B, C, D. You're going to use a different formula because of how you have your diagram. So in this case, let us use the same thing. O AB, like from the origin, A, B, and so on. So you want to calculate this one. This is our BC. That is our installed KVA, this one, BC. So BC is simply equal to what? The difference Q1, the whole of this AC, the whole of AC, minus this part, AB. Just like that. AC minus what? AB. We're done. So if you can find AC, you find AB, you subtract. You're done. So using what? Trigonometrical ratios. All right? Using trigonometrical ratios or trigonometry concept in short. Your trigonometrical ratios. I don't know what are you going to use Pythagoras theorem. If it is to be applied, let it be like that. You can have it that way. So OA is what? The true power from the original values. As you can see, it is same. Even if after the capacitors has been installed, it is still the same. It is not affected. But our apparent power S1, which is our OC, this one, OC, is our load KVA, this one, load KVA, which represents what? S1. Then S2 is now our resultant KVA, which is our OB, right? AC and so on can also be calculated. So that is it, guys. We can calculate this by using this formula, using your trigonometric concept, or we can calculate another method or another way that we can use is this way to find our BC, the same BC, this one, which is our KVA rate, kilovolt ampere reactive rating of what? Of the capacitor bank. We can also calculate the same KVA reactive from this formula, which states that it is going to be resultant, take note, resultant kilovolt ampere, this one. From this idea, I want us to see the idea. I'm not done with the formula. I'm going to finish it. I want you to see where it is coming from. This is the part that we need, this one, BC. So from our vector concept, we can simply take the resultant, this one, minus the load. So resultant minus the load from the vector concept, it can give us our BC, which is the rating of the capacitor bank, our kilovolt ampere reactive. So we are going to subtract the load KVA. So this one, I have to explain it as a separate part. This one, I must explain it. It's another formula that can be used, or you can use this part. Guys, what you just need is to find BC. This one, according to our diagram, this one, this BC. Using any mathematical way, but this one, it's a phasor calculation, this one. It's a phasor calculation. It is the phasor sum. So it's a phasor calculation, this one. Remember, it is the phasor sum. This difference that you're talking about, it's from a phasor. So meaning to say, you must be able to apply your complex numbers to use this method. It is very, very important. And there are adjustments also to be done when you're using this calculation. So I would just opt you guys to use the trigonometry concept. You work with your trigonometry. Remember your SOHCAHTOA working with a right angle triangle. As you can see, we are having a right angled triangle. So when you are given an angle here in a right angle triangle, this side is going to represent our opposite. The hypotenuse always facing what? This right angle that we see. And definitely this will be adjacent. Our angle and 90 degrees, they are adjacent to each other. And remember your SOHCAHTOA concept. All right. Remember all this part. SOHCAHTOA sine, opposite over adjacent, cos adjacent over hypotenuse, opposite over adjacent for what? For a tan. This is the concept. This is the concept, guys. So I want you to work with that. So here it is simply the same. AC minus BC, which is Q1 minus what? Q2. If I can have Q1 and have Q2, have these ones, I have these values, then it simply means I'm done. From that case, it simply means you're done. So I want you to work with these basics. In our next class, we are going to be working with an example or examples now to apply this concept using both calculations or ways. So like I said, guys, make sure that you become part of the membership so that you do not miss any calculations that we are going to be having till we meet again.